Oh yeah, this is topic 9.3 now. I think it's just called interference. Interference. So interference is really what happens when two or more waves combine together. When they combine together, and remember that from springs, it's not that their amplitudes add together, but their displacements. So you've got a wave like this and a wave like that. So at this point here, the amplitude of this one looks, if that's 10 up here, the amplitude of this one looks like about 7, the amplitude of this one looks like about 9. Overall, that gives us a 16 at that point in some case. So the amplitude is 10, the amplitude is 10. We're not adding together to get 20, we're adding the displacements at any point. At this point here, this time here, we've got, it looks like a displacement of say -7 and a displacement of +4 maybe. That will give us an overall displacement of -3. So we're adding together the individual displacements. That's what interference is. Two or more. Okay. So we talked about the single slit diffraction pattern and then the double slit interference pattern. Let's just look at those again. So single slit, that's again putting the marks on the axis to start with. So our single slit diffraction looks like this, much lower, much lower. So there's our single slit diffraction pattern. A double slit interference pattern. You need to be able to draw those patterns fairly accurately. So single slit diffraction, central max twice as wide, and much in the mark scheme it often says, don't give the mark, unless their maximum is, I can't remember, less than a fifth or something, but it's way, way less. Alright, so it's not up there, it's not just less, it's way, way less. Come on in. Whereas with the double slit interference pattern, they're all essentially the same. This one is twice as wide as all the others are the same. And these ones are all the same width, right? So that's so minima at 0. And again, I said last lesson that seems a bit fussy, but if you're not touching the axis there, then you'd probably lose a mark for it. Okay. These ones as well touch the axis, but for a double slit. All maxima the same width, all same height. I think I wrote this last time, so nothing new there. Maybe decreasing slightly, and we'll sort of talk about that. Okay. So, in terms of producing this experiment, it becomes important to look at to understand Young's double slit. Young's double slit experiment. Okay. If if I just have two lights giving off waves, so two separate lights, there's going to be no interference pattern. Will there be no interference? Well, interference is just when two or more waves join together, so there'll still be interference, but there won't be any patterns of nodal lines and maxima and minima, because those two light sources, so let's should make them look like they're light sources here, so we've got light sources giving off light there. And so, because they're not coherent, they're not in phase, they're just producing light on their own. So it's only going to happen, it's a bit like in the ripple tank. If I've got dip, 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 dip in the ripple tank, and we can do that. I'll bring the camera over here in a moment, probably out of the screen there. Okay, just swinging you around to have a look at the ripple tank and zoom in a bit on that. This out first, zoom in. Oh, I get around the wrong way, don't I? Okay, lights off. Okay, so what we've got here is the 2-point sources dipping in. Each of them are generating circular waves. You can see the waves heading out there. And those two waves are then interfering. Can't really see any interference patterns in that with nodal lines and so on. Sometimes you can. I think the screen's a bit dirty. Maybe I should give it a wash before I set it up today. But you can see those overlapping circles. Hopefully you can see that all right from there. We'll have a look on the ripple tank simulator shortly and just see what we get. I can't really see any nodal lines out of that lot there now. Those two sources are dipping in and out of the water in phase. We call it coherent, because they're both linked together. But if I was dipping something into the water and someone else was dipping something into the water, then they're not necessarily of the same frequency. There's not necessarily a constant phase difference. So these two are pretty much dipping in together. So they're generating those waves, and a point which is going to be maximum disturbance constructive interference, maximum constructive interference, a maximum, is going to remain a maximum. Whereas if we're just dipping, generating the waves independently, then the whole pattern is changing. And that's what I'm saying here. Oops. And that's what I was saying here, that if you've got two separate sources, and I've asked this question before, you're not going to get any interference pattern. You're going to get interference, but there's not going to be any pattern because things are going to just keep changing because those two light sources aren't together. They're not coherent, they're not in phase, they're not a constant phase difference. So, in order to view a double slit, we wanted to have those two double slits effectively linked together. And so that was what Young did. Here's the pens. In Young's experiment, he had a light source, one light source, going through a single slit, and then that going through a double slit. Right? So the light would go through this single slit. So we've got light coming through here, going through the single slit, and then as it got to those, the two patterns then were overlapping. Right? If we didn't have that single slit in between, then light from this side of the light and that side of the light are effectively, reaching those slits at different times, and you're not going to get that same concise pattern. Okay? So the purpose of the single slit is to make the light arriving at the double slit coherent. In English, coherent is a word that means easy to understand. I'm not sure if this is coherent or not, or whether I am, but it sort of means the same. Coherent means all together. So it specifically means having a constant phase difference. When the light comes from here to there and from here to there, those distances are about equal, but they're not exactly equal. Certainly not when you talk about the wavelength of light being 10 to the minus something by 10 to the minus 7 metres. So this might be 3 centimetres here and 3.1 centimetres here. Yeah, close enough. But that's still hundreds or thousands of wavelengths different. So they're not necessarily going to be in phase, but it's not changing. So if this is 115 wavelengths and that's 114.2 wavelengths, then it's not changing. And so there's always that constant phase difference. So coherent means a constant phase difference. Now we're normally assuming that these two waves are generating the waves together. Not necessarily the case, but it doesn't really affect what's going to happen. And so again, whether it's two things dipping in the water or a double slit, we still get these two semicircular patterns coming around here. I'm trying to draw them with a constant wavelength, and the same constant wavelength here. So it's not super accurate. We'll have a look again shortly at some of the Walter Fink ones, which do show them very clearly. Okay, let's go for colour. So if I call this A and this B, the centre of the pattern is out here. Right? Anywhere along the centre of the pattern, so a point P along the centre of the pattern must be the same distance from A and B. So AP is equal to BP. So AP is equal to BP. Often what we talk about, and we mentioned this last year as well, is the path difference. Path difference is like constructive interference, destructive interference, another really important term to use. And so anything to do with diffraction, and particularly to do with interference, at some stage you should mention path difference. Path difference is 0. What's the path difference mean? How much further does the wave from A have to go compared to the wave from B? Nothing. It's the same distance. Okay. So the path difference is 0. So if the wave from A is a peak or a crest at that instant, at that time, so A and B are lined up. And so the total is just going to be like that. So we've got like double peak, double trough. Which of course is constructive interference. And that corresponds to rough water. Bright light. Loud sound. So whether we've got water waves going through here, whether we've got light waves going through here, whether we've got microwaves or sound waves, it could be two speakers. It's certainly not two people speaking because their sounds will be quite different. If I've got two speakers connected up to the same signal generator, well, first of all, it's only going to happen if they're giving the same note. See a constant note, sending out waves like that. At some points we're going to get nodal lines. Right? So that's along the centre of the pattern. And the centre of the pattern will always be a maximum because the path difference is 0. If the two sources weren't in phase, let's say they were exactly out of phase, so 180 degrees out of phase, pi radians out of phase, then you would have that as a peak arrives from here, a trough will arrive from there, so the centre of the pattern would be a nodal line. The whole pattern gets shifted around, and we can do that when we have a look at the one on Walker Front. Okay. If we move away from the central line, so that means something like that, then I won't put it there because it's not directly out, it could be, but there's AP and there's BP, clearly they're no longer equal. So AP minus BP is not equal to 0. Path difference is not equal to 0. Okay. So depending on what the path difference is, if the path difference is exactly half a wavelength and they're in phase when they start, then the two waves will be exactly opposite. So you'll always have a peak with a trough and then a trough with a peak, and so we'll get cancellation. That's where the nodal one comes from. All right? Two waves of light will be opposite. So you've got from A and from B. It's going to look more like that. So at all times, here's our central. So at any time we've got here a -5 and a +5, +5 and a -5, a -1 and a +1, a 0 and a 0. So the total, overall, is nothing. By nothing, it doesn't mean all the water's going to go. It just means that there's no disturbance, no displacement from that mean position. It doesn't mean that all the air is going to go. It just means that the sound, and with sound waves, you've got bigger pressure and lower pressure, compressions and rarefactions. All it means is that at that point, all of the air is at the same pressure, so there's no rarefactions and compressions. And with the light, there's no light. Okay, so this means cancellation. So destructive interference. So flat water, no light, it's a dark light I suppose, no sound. Alright. So there's for path difference of 0, there's for path difference of lambda on 2. If you've got path difference of lambda, then you've got the same, except that one's moved along by lambda, and you've still got peak and peak, peak and peak, trough and trough. Exactly the same. Double peak, double trough, double peak, double trough. If the path difference is lambda on 2, yep. 3 lambda on 2, that means 1.5 wavelengths. So again, it's moved along by a wavelength, but this peak now coincides with this one. And so you've still got peak and trough, trough and peak and trough, and it's still got total cancellation. So half or 1.5, 2.5, etc. in destructive interference and nodal lines. Overall, just about leave that pattern there. So if I draw that accurate, I have a variable, we can look at it on the computer in a moment. You know, this and this should be the same. They don't quite look at it. Let's bring that one in a bit. And let's set it on too wide, is it? Right, each of these maxima should be the same width. Alright. So this is the central max. Path difference equals 0. This is the first nodal line, the path difference, and PD is a funny abbreviation. Not necessarily funny, but it can stand for a few different things. You know, in teaching it often stands for professional development. But in physics, there's two things. There's path difference, or there's potential difference. So when you're talking about voltages in circuits and so on, we often talk about potential difference. There's not many situations where it's going to overlap, but you know, just be aware that here with waves we're talking about path difference. How much further it is from one source than the other in the electric circuit, potential difference. Okay, so the path difference here is lambda on 2. Here is also the first nodal line. Potential difference is lambda on 2. Outside here we've got the first max. Sometimes it's a little bit ambiguous. By first maximum, I don't mean the central maximum. So the first maximum away from the middle, and the path difference is lambda. Path difference is lambda. Here's the second nodal line. The second nodal line, the path difference is 1.5 wavelengths, and so on. And then here we've got the second max, and the path difference is 2 lambda, and so on. Okay. Let's have a look at this. I thought I had all the effect up here somewhere. Let's see it. Let's find it again. You should have this site on your laptop and you should be referring to it often. It just shows so many aspects of physics and of our course so well. Come on. Okay. So this is two sources dipping in together. Now it's exactly the same as if this was a flat wave, straight wave, and then then a double slit. All right. And in fact, what's happening between them is exactly what happens with the with two waves on a spring. You still on there, or have I walked out of the screen here now? All right, sorry. Okay. Let's zoom in a bit on that. Got it the right way this time. Okay. So this is just a lovely applet for helping you to understand interference. So we've got the two sources here. This red line is in the middle, and the point, the pink purple point that's shown there now, it tells us the difference of path lengths. That is, the path difference is 0. All right. So therefore, constructive interference maximum amplitude. Okay. If I move that point anywhere along there, then I find that the path difference, of course, is 0. So by moving that point, anywhere along the central line, the path difference is 0. But as soon as I move off there, the path difference is not 0. See the difference in path lengths there? Down the bottom, hopefully you can read that alright. And so if I move, well, let's just freeze it. For example, pause at. So here's, let's call this A. Let's do it again, and I'll do it just as it generates the wave. And now, alright. So from this point here, and I'll come in, so I'm a whole number of wavelengths, so it didn't have to be. So here, it's about to generate a dark line, which will assume the dark line is the crest, and the light line here is a trough. So about to generate a crest, here's a trough, here's a crest, here's a trough, here's a crest, here's a trough, here's a crest. So the distance between two black lines is a wavelength, or the distance between two light lines is also a wavelength. From here, I've got one wavelength, two wavelengths, three wavelengths. From here, I've got 1, 2, 3. Note that the two sources are in phase. They're both generating crests at the same time, and of course troughs at the same time. I'll keep that frozen. Now if I move off here to this point here, this is a point on the first nodal line. From here, I'm 1 wavelength, 2 wavelengths, 3 wavelengths, and a half. From here, I'm 1, 2, 3. So the path difference is half a wavelength. That's what it tells us there. And it's destructive interference, it's minimal amplitude, it's on a nodal line. So these curved lines here are nodal lines. The red curved lines are the anti-nodal lines, or the lines of maximum interference. And so you've got that there. Now I can change the pattern, and the qualitative things that happen are exactly the same as what happens with single slit diffraction. If I move the sources closer together, then the pattern spreads out. That's what happened with diffraction. Or if I increase the wavelength, same thing happens. Let's look how many nodal lines we've got. Remember, the reds are the maxima, so there's 2 nodal lines each side. 2 nodal lines each side. 4 nodal lines altogether. Alright. Let's make the sources further apart. So instead of 10, let's make it 20. So now we've got more nodal lines. The pattern is, so more nodal lines, but they're closer together, so the pattern is closed up. Alright? I could have similarly done that by, if I increase the wavelength to 8, we should go back to where we were. Alright? So we've still got the same number, 2 nodal lines, in each one. Okay? Let's go back to 10, the original diagram, 10 and 4 I think was our original one. 10 and 4, resume. Okay, so yeah, there we are on that nodal line. I want to pause it as it's generating a peak again. There's trough and peak. Close enough. Alright, so as I move to here on this red line, at the moment, so I know it's an anti-nodal line. It tells me there's one wavelength path difference. Let's count them out. From here we've got 1, 2, 3, 4. From here we've got 1, 2, 3. 1 wavelength path difference. Next maximum way out here, I'm 1, 2, 3, 4, 5, 6 wavelengths from here, and 1, 2, 3, 4. So there's 2 wavelengths path difference. And again, if it's a whole number, an integral number of wavelengths, then we'll get constructive interference at a maximum. at this point here, let's drag this across, at this point here, I'm on that second nodal line. First nodal line, second nodal line. First nodal line, path difference of half a wavelength. Second nodal line, path difference of 1.5. Let's count. 1, 2, 3, 4.5. 1, 2, 3. The difference is 1.5 wavelengths, therefore opposites, therefore cancellation, therefore destructive interference, therefore nodal line. Okay? Have a look at that. Alright. Let's look at the geometry of the situation now. Let's see the blanks so they're consistent. On the first, nodal line I've got A, P, and BP. Okay, I can put a line across there so that this bit is the same as this bit. And so the path difference is really this bit here. Okay? This one is doing this length, this one is doing that same length plus this extra bit. Okay? So right over to the other side. Oh, so I need to move you back. Oh. Sorry. Let's just go through that again. So if we're on the first nodal line at P, then the wave is going from A to P and B to P. Clearly those two lines are not the same length. In fact, the path difference must be lambda on 2. If I put a line across there, then that length is the same as that length. And this extra bit here is the path difference. So, this angle here is the same as this angle here. We've got that tan of theta. So, let's say this distance here is x, and this distance here is L. Tan theta is equal to x on L. L and x and theta. Also, from our other triangle, this is D, the source separation. This is the path difference, which is lambda on 2. And this is the same theta. So we've got here that sine theta is equal to lambda on 2 on D, or lambda on 2D. Okay? So we've got those relationships there. So sine theta will equal lambda of d So that's our angle for the nth maximum. So be careful whether you're looking for maximum or minimum. It's in your data booklet. Sometimes I use a capital D instead of a capital L, but that's really showing, it's the same thing. I think in the data it's just that x equals lambda d on d, and that would be for the first, the distance to the first maximum. Okay. The papers are back there. So I was just talking to the camera So what we're getting at is a combination of that. So this is the single slit pattern, and that becomes like an envelope to the double slit one. So we're going to get a double slit pattern inside here, which only goes up as far as that. Depending on how big the single slit is compared to the double slit, often it might be 10 times as big. So we're going to get 10 maxima in here before we get to the land, where B and D are outside and different by a factor of 10. And so sometimes they'll give you that pattern and ask you to work out, given what B is, what D is, or given what D is, what B is. So, you know, we might get a pattern like this. So something like that. So you've got the single slit diffraction pattern as an envelope holding that double slit interference pattern. And from the relative numbers there, how many maxima do we get here? In my case, 1, 2, 3, 4, 5, 6, 7. So what that would tell me is that D, the separation of the two slits, is 7 times B, the width of the slit. That's become a fairly common question over the last few years, so make sure you're comfortable with that. The textbook shows that really nicely, very similar diagram to what I've drawn as well. Okay, multiple slits. That's all right. You need to be good at drawing those single slit and double slit patterns. Again, you know, I've tried to make, not very well, let's try that again. Okay, so I'm drawing a double, so 2 slits. A double slit pattern has all maxima the same width. Alright, there's my central one, the other one is the same. So like that, like that, like that, like that, like that, like that. Okay? So they're all the same width and all the same height. Right, so something like that. That's 2 slits. Okay. As we add more slits, so 2 slits is like there and there. Alright. 3 slits still the same separation. So if I just put another one in the middle, the whole thing will change. But if I've got that same distance there, so this is D, this is D, and this is D, right? We still get cancellation at the same points. So our pattern, and we'll summarise this shortly, our pattern is still going to be exactly the same, except, so our minima are in the same place. So I'm just putting these lines straight down from above. But what happens is the minimum become a bit sharper. Not much difference between 2 and 3, and you often get little, or not often, and you get little secondary maxima in between. So I'm going to make this sharper and more intense. So the maxima are at the same point. Let's make these last a couple bit bigger. Okay, a couple of things. I'm just not sure that my diagram's covered it. Let's go on to 10 slits. Clearly, I can't draw all the 10 slits across there because they're still the same height. Our maximum and minima are still in the same positions. They're still the same width, but as we get more and more slits, they become sharper and sharper and more intense. 2 slits, that's through a certain amount of light. 3 slits, that's through a bit more. 4 slits, that's through, so 10 slits, that's through a lot more. So we've got, very intense and some secondary maxima, very intense and sharp. And same here. They're all supposed to be the same width. So, there's a number of things to note from this. That the positions of the maxima and the middle of the minima, so probably the positions of the maxima, are in the same places. Central max, first max, second max, third max. Exactly the same as for the double slit. So therefore, sine theta equals lambda on D. They become much sharper because, when you're not at the maximum, then you've got a lot more sources cancelling out. So you've got little bits. There are subsidiary maxima there. In fact, the number of maxima, where there's 2 slits, there are no subsidiary maxima. When there are 3 slits, there's 1. Doesn't look like 1 there, that one there shows it. It's n minus 2. You don't need to know that. You need to know that they're sharper, that means narrower, they're more intense because there's more light coming through, and they're in exactly the same places as the 2 slit maxima. Sometimes the question will say, tell me 2 different things, 2 things that are different about the 6 slit pattern compared to the 2 slit pattern. They're sharper, the maxima are sharper, not just it's sharper, the maxima are sharper. That means they're narrower and not spread out over a wide region. They're sharper. They're more intense. They're brighter if it's light, and they're in the same positions. And there are secondary maxima. For a 6 slit, there would be 4 secondary maxima. So it's something you could throw in. I don't think you would need to know the number of secondary maxima, but just that they exist. That could give you another point. But the main ones are that they're more intense and they're narrower or sharper, and they're absolutely in the same position. So just like that. So, let's see the maximum. N minus 2, very small secondary maxima. They're not all equal, it doesn't really matter, you know, just to mention secondary maxima, you know, can get you a point, but you wouldn't even need that. So you've got a lot of lines together with the diffraction grating. Diffraction grating, in the extreme case of a multiple slit, you might have 1,000 lines altogether. So what we should get is that the maxima are really sharp, they're still in the same positions, and they're quite intense. I've got a diffraction grating, I'll show you that in a moment. So I'll just set this up. Okay, so the laser light is shining through the diffraction grating. All I can see is the central maximum there. Move it a little bit sideways. Yeah, not not sure if you can see over on the left hand side there. So on the far left hand side of the screen, I'll point it out on the board, I'll block it now. So here's a spot here. Any sort of expansion, that blurring, that is just from the laser light spreading out. So we've got our first maximum there. If I continued it around, we might be able to see a second one. Oops. That's it, let's go the other way. There's a central one. Yeah, oops. There's one right near the TV screen there now as well. Right, so we're seeing the first maximum on both sides, and from that we could work out the we can measure that distance accurately to the first maximum. From that, we know from the grading. I'll turn it on. The light back on. So the diffraction grading is just the same sort of, it just looks like a bit of plastic. It's actually a diffraction grating. It tells me on here there are 600 lines per millimetre. So 600 lines per millimetre. Alright, so if you get a question on a diffraction grating, the first thing you've got to find is what D equals. D is the separation between the lines. Can you imagine that 600 lines in a millimetre? How on earth do you do that? And I'm not sure what they are on a DVD or a CD, but you've got lots of parallel grooves. And that's why when you hold a DVD up to the light or something, you can see colour, you can see rainbows effect, and we'll talk about that as we go on, because you've got lots of lines straight together. And when I look at this, when you presumably can't see it, but I can see rainbow colours in that plastic bit there. Okay, so if there is a question on a diffraction grating, then your first bit is to find out what D is. And the number of times this gets mucked up. So 600 lines in a millimetre. Alright, so what's D? It's pretty small. Alright, so we want 1/600th of a millimetre is the separation. So that becomes 1/600th is 1.67 by 10 to the minus 3. That's how many millimetres it is, or 1.67 by 10 to the minus 6 metres. Right. 600 lines per millimetre. That's a pretty typical one. And so once you've got D, then you can use your equation there, that we still have that up there, that for the max, double slit. And again, the positions of the maxima in the double slit are the same as they are for a diffraction grating for a multiple slit. So for the maxima for two slit, sine theta equals lambda on D. The wavelength, I think I said 633 nanometres, I'll just check that. 633 nanometres, so so I just want a rough idea. Maxima at sine theta equals lambda on d, 6.3 by 10 to the minus 7 over 1.67. Okay, so what's that going to be? 4 lots of that, pretty much 4. So 4 by 10 to 10 to the negative 1 was 0.4. So the reason I hesitated there was I thought I was going to get a sine theta bigger than 1. If sine theta is 0.4, theta equals, I'm not sure, 22 degrees. Yeah, I won't bother calculating it, but it's something like that, probably more. I know that sine of 30 is 0.5, so it's, I don't know what it is, 23 degrees. We're 5 metres away. And that angle is 23 degrees. So x is equal to 5, well that's 5 here, so we need to use sine and tan, but roughly we're expecting about 2 metres. I think when I had the central maximum here, the other one was just off the screen, both sides, so that's going to be a fairly reasonable estimate for it anyway. So x is approximately 2 metres. So that's, I haven't done any calculations there. I think if I turn off the camera, then it becomes a separate file. I don't have to work that out, pause it and do things like that. So I think we just keep on going with the one video. So that that fits in reasonably well. So that gives us the use of a diffraction grating. So if you've got a combination of, for example, red and blue light, what we had was just the red laser, but if I had red and blue together, then they would both have the same central dot, but the blue central dot might be here and the red central dot might be there. So it will get separated out more. Red being a bigger wavelength will be further away because sine theta is equal to lambda on d. So if lambda is bigger, then sine theta is bigger. So you can separate them. With red and blue, they would separate by a considerable amount. But in some situations, you've got 2 wavelengths. I mean, see, even things like with the lines of the sodium spectrum, you've got those, whether you remember the sodium spectrum, you've got 2 lines in the yellowy-orange region which are very close together. If you put that light through a diffraction grating, then we can separate them. All right? How much can we separate them? And that sort of comes into the next bit where we get into resolution. Not sure what more we need to do here. Still thin. That's a long topic. Still thin film interference. So, e.g. blue, you've got red and blue together, and you've got blue and red, and you've got blue and red, and the separation will be even bigger. Let's use it so I can show you the second one as well. So let's both sides. You've got red on the outside, blue on the inside, and further along you've got blue here and red. So you've got the centre, I'll put the dotted line down there, that's the centre of the pattern there, red and blue together in that. You've got some separation there and a bigger separation here. Sometimes they'll say, you know, the angular separation of red and blue on the second, so the first maximum or the first order maximum, second order maximum. So the separation of red and blue on the second order maximum is such and such. What's the difference in wavelength, or what's the how many lines per centimetre are there, or something like that. Okay. But that 600 lines per millimetre is a typical one. Okay, one more bit. Gee, this has been going for a while. One more bit. Thin film. Thin film interference. Okay. Interference, combination of more than one wave, of two or more waves, which is going to produce constructive and or destructive interference, producing maxima and minima. That's what interference is, combining together of two or more waves. Thin film. You've seen that before with soap bubbles. You've seen it before with Glad wrap, you know, really thin plastic sheeting. You've seen it before with a film of oil on a puddle, where you sometimes see a rainbow effect. Right? Same thing here, and this is going to be why it happens. And this is particularly with light, you know. I suppose it could happen with sound or micro or something, but well, and it does happen with radar. I'll get to that shortly. But okay, thin film interference. So when light shines normally, and normally means perpendicularly, okay, so if light comes in, I'm showing it at a bit of an angle, just so that we can see the difference there. It comes in, it actually gets refracted back, and then out. I'll bring it in a bit more of an angle so we can see the refraction there. So it comes in like that, it's bent towards normal, it's refracted, and then out like that. Alright? Some is reflected off the top surface, and some is reflected off the bottom surface. Those two rays of light look like they are quite separate, but you know, we're talking about, you know, a fraction of a millimetre thick. Those two rays of light are effectively together, and so they combine. All right? But they've had a path difference. The path difference is this and this. All right? This one has just got reflected off the top, this one's got reflected off the bottom, it's travelled further. So once again, the interference, what happens with the interference depends on the path difference, and that's what you've always got to remember, path difference. It may produce constructive interference, it may produce destructive interference, or somewhere in between. It's not just one or the other, but the extremes are constructive to make, well, in fact, constructive is anywhere where it adds together, but the extremes are a maximum or a zero, a minimum or a zero, which is a zero. Okay. reflected off the top is A, and what's off the bottom is B. Okay? B has travelled further. Now, from the angle we've got there, it looks like we've got all sorts of sine theta and everything to work out, and that's what we used to have to do. But for the last few years, it's only been coming in normally. So therefore, if I just did coming down, coming back, you wouldn't be able to work out what's going on. But there's the two ways: one coming off the top and one coming off the bottom. The path difference is just 2t. T is the thickness. Again, we're talking about the thickness of a soap bubble, the thickness of a sheet of Glad wrap. It's very thin. So depending on what 2t is, we'll decide on whether we get a maximum or a minimum. And clearly it depends on the wavelength of the light as well. So what we want is the thickness of the film in terms of wavelengths. However, there's a trickier bit. You may remember back to when we looked at waves on a coil spring. When the wave went in and it was being held at the other end, it got reflected upside down. But if it hit a boundary which was less dense, where the speed was increasing, then it gets reflected right way up. Okay? So you've got that happening as well here. When you're going from a less dense to a more dense, it's reflected upside down. When you're going from a more dense to a less dense, it's reflected right way up. And so that's going to change things. Right? So we need to take that into account as well. So, when a wave is reflected off a boundary, it can be reflected right way up or upside down, a phase change of pi. So again, a wave on a spring coming in, let's have the wave with a wave on a spring coming in and hitting a fixed boundary, it gets reflected upside down. So that's a more dense medium, it's reflected upside down. The sharp edge comes first, so it's going to be like this. Right. And we've seen that lots of times. I'll put a line under that just so we don't get confused with what's happening here. If it comes in here, same wave coming in to a free boundary, so one that's able to move. So this one is reflected upside down. Phase change, and phase is the angle. It's changed by 180 degrees, by half a cycle, by half a revolution. So of pi radians, or 180 degrees. It corresponds to a path difference of half a wavelength, but the phase, we're talking about the angle. And this one's reflected right way up. So we've got, So this is coming in here. I've deliberately drawn them asymmetrical because you've got a gentle one and then a sharp bit. And so the sharp bit is first, the sharp bit comes back first. And generally the aperture is going to be a bit less too, because there's lost a bit of energy. That looks like it curves all the way through there. So something like that. Alright? In this one we're reflected. Right way up, same way up. Phase change of 0. Okay. With the thin film here, we've got 2 reflections. So if we're going from air to water to air with a soap bubble. Right? So we're talking about refractive index 1.0, 1.3, 1.0. First reflection is there, the second reflection here. The first reflection is 1.0 to 1.3, therefore phase change of pi. It's going from air into water, it's going from less dense to more dense, it's reflected upside down. The second reflection is 1.3 really, to 1.0, therefore no phase change. Alright? Total path difference is 2t, but the wavelength in that medium is not the same as the wavelength in air. So the effective path difference is 2nt. Since we have a phase difference of pi, therefore minimum at 2nt equals 0 or lambda or 2 lambda. Maxima at 2nt equals it gets a bit tricky here because n can, sometimes stand for which maximum you mean, or n could stand for which the refractive index. So n is standing for the refractive index here. So we need to worry about what's happening at each interface. They're different. One's giving a phase change of pi, the other's giving no phase change. So even if there was zero difference, even if the thickness was effectively zero, we'd still have that phase change and we'd have a minimum. So a minimum at 0, lambda 2, lambda, etc., and a maximum at the half wavelength. But if we have, let's have, say, air, oil, and water, let's go 1.0, 1.2, and 1.33. Alright? So there's reflection 1, there's reflection 2. At 1, we've got 1.0 to 1.2, therefore phase change of pi. At 2, we've got 1.2 to 1.33, therefore phase change of pi. So they've both had the same phase change. Well, you're always going to have a phase change of pi or nothing. So, you know, if there is a phase change, it's always going to be the same, 180 degrees or pi. Given that in both cases we've gone from less dense to more dense, 1 to 1.2, 1.2 to 1.33, less dense to more dense, both of them are reflected upside down, so we don't need to worry about it. Alright? So now the path difference equals 2t effective, path difference equals 2nt. So therefore minimum at 2nt equals, we're going to get a minimum when there's cancellation. We don't need to worry about that extra lambda on 2. 2nt equals lambda on 2, 3 lambda on 2, 5 lambda on 2, etc. And maximum at 2nt equals 0 lambda, 2 lambda. There are formulas in the data booklet for this, but you know, they can be confusing and people are always marking up, well, what's n and what's m and what's t. You know, to go back to first principles and say, alright, is there a phase change? So draw a little sketch like that. They'll give you the refractive indices. Well, you know, if they don't in this one, it doesn't matter because you know it's air to water, water to air. One's one way and one's the other way. In a situation like that where you've got a layer sitting on water, an oily film on a puddle, then yeah, that happens. And so, you know, rather than just blindly using the formula and fair chance you're going to use it incorrectly, just try and work out what's going to happen here. What's our path difference? You know you're going to get cancellation when the two waves are opposite. Well, they could be opposite just because of the path difference or because of a phase change as well. So you've got both things coming into it, so it becomes a bit tricky. And most students get them wrong. So if you can get some of these right, then that picks you up, and that's all you're trying to do. You're just trying to beat as many of those other kids around the world as you can. So yeah, a bit tricky. Look carefully through that and see if it makes sense. That hasn't explained. Well, let's talk about something else first. With aeroplanes, sometimes they have an anti-reflective coating. Sunglasses, they have an anti-glare coating on sunglasses. They have an anti-radar coating on aeroplanes. And so, as the radar hits the plane, it hits the top layer of the plastic and the bottom layer of the plastic. And if those two reflected waves cancel, then what comes back is nothing. So they can be invisible under radar. unfortunately, that will only work, that will change depending on what the wavelength is. With anti-glare coatings on sunglasses, you know, again, what comes back depends on the wavelength. But for some wavelengths, they will cancel, and you won't see anything. And that is why you see the puddles, in puddles with an oily film or a soap bubble, you see the colours. Because when the light is shining on, you know, on this bubble, as it gets reflected, you're going to get maxima at different angles. You know, we only worry about coming straight in, but at different angles, you know, for an angle of 30 degrees, it may be that you get a maximum of green and a minimum of red and blue. At 32 degrees, you get, you know, a different maximum. So as you're looking at that CD, well, CD came from before, but the same thing. The different colours have different wavelengths, so they have maxima and minima at different points. So in the bubble, you know, as we move around, our eyes see the maximum of red and then the maximum of green at different angles, and minima at different angles as well. And so that's why we're seeing the rainbow of colours, because the different colours have different wavelengths and therefore have maxima and minima at different angles. Okay. That's it.